This is a continuation of the introduction to MathQuest 251, the three-dimensional geometry. Sorry about that awkward cut there. My dog started barking and I accidentally hit the stop instead of the pause, so my apologies. But at any rate, we were starting to say, hey, how would we actually plot a point in 3 dimensions? So here's an example. If I'd like to plot the point P, 3, 4, 6, I'm going to draw those dotted guidelines just like we saw in the picture right above this. And I'm going to start by saying, all right, if I begin in the xy plane, x is 3, y is 4. And by the way, I probably should have mentioned, we always give the point in the order x, y, z. So I'm going to draw the base of the little box that's going to give me the guidelines. And when I draw my dotted lines, the most important thing to remember to get the perspective right is always draw your lines parallel to the axes. So I'm going to draw a guideline horizontally, parallel to the y-axis, and then another one at an angle, parallel to the x-axis. So there's my guidelines for the bottom of my box. Z is 6. So next, let me put the guidelines into the YZ plane. This is the easiest one. I'll go up parallel to the z-axis, and then over parallel to the y-axis. Over here in the XZ plane, I have to get that perspective again. So first of all, I'm going to show that I'm going to kind of come parallel to the x-axis, and then vertically parallel to the z-axis. Finally, I need to get the top of my box in place, so I'm just going to kind of finish drawing these lines. I need these same 2 lines up here. So kind of making sure things line up and stay parallel to the axes. And then this point on the corner here, with perspective, is my point P. P, remember, was the point 3, 4, 6. Just for a little practice, we can actually label all of the other corners of the box as well. For example, this first corner was at x equal 3, y equal 4. And we hadn't gone up at all, so z would be 0 there. This point is in the yz plane, so x is 0, y is 4, and z is 6. This point is in the the xz plane, so x is 3, y is 0, z is 6. And although I did label these just as 3, 4, and 6 on the various axes, I could actually do a little bit better job and give all of their coordinates. This x-intercept would really be 3, 0, 0 if I wrote all the coordinates. This y-intercept is 0, 4, 0. And this z-intercept would be 0, 0, 6. All right, so that's how we would locate a point in 3 dimensions. As you can see, it's much more time-consuming than trying to plot something in just 2 dimensions. And for that reason, it's really not something that we're going to do by hand much, if at all. It's just not feasible. In fact, if you can imagine how you first learned how to draw graphs in 2 dimensions, where maybe you plotted 6 or 8 points to see what it looked like, as you can imagine, that's just not something we could do here at all. So instead, as we start looking at what graphs look like in 3 dimensions, we'll again look for patterns. We'll say certain equations lend themselves to certain types of graphs. But ultimately, we're also going to find that having a good 3-dimensional grapher is going to become very important to us for exactly this reason. It's just too difficult to graph things by hand unless we already have a pretty good sense of what it's going to look like. So, speaking of having a sense of what it's going to look like, let's take a look at a few formulas and graphs where our experience in 2 space can do a really good job at predicting what's going to happen in 3 space. First of all, we'll take a look at the distance formula. I suspect this is one you've all seen probably many times. But if we've got 2 points, P1 and P2, then the distance formula, the distance d in between them, is just the square root of the difference in the x values, x2 minus x1 squared, plus the difference in the y values, y2 minus y1 squared, all under the square root. You may, in fact, even recognize that as just a version of the Pythagorean theorem, but I'm sure you've seen that formula before. Here's what I mean by using patterns to extend things into 3 space. Let's suppose I now have 2 points, P1 and P2, in 3 space. And again, my goal is to find the distance between those 2 points in 3 dimensions. The only difference between the points, of course, here and here, is that we now have a z component as well. And all that's going to do is, using the same pattern, add a 3rd term under the radical for our distance formula. So we'll still have the square root of, we're going to start out exactly the same way. But now we'll just add a 3rd term, z2 minus z1 squared. So I'll mention again, we couldn't draw a 4-dimensional point, or 2 of them, but does it make sense to talk about the distance between 2 4-dimensional points? It actually does, because you would just have that 4th term under the radical. We could do the same in 5 space or 6 space. So mathematically, again, we can do mathematics on higher order spaces, even though we can only draw up to 3. The next line talks about the midpoint formula, again, one that I'm sure you're familiar with. So if I've got 2 points, P1 and P2, the formula to find M, the midpoint between those, we just take the average of the x's, so x1 plus x2 over 2, and then the average of the y's, y1 plus y2 over 2. Again, I'm sure you can see that this is easily extendable into 3 space or even 4, 5, 6 space and so on. If I've got 2 points, P1 and P2 in 3 space, and once again my goal is to calculate the midpoint halfway between those, I just take my established pattern and I use it to create a 3rd coordinate. z1 plus z2 divided by 2. All right, so a couple familiar formulas extended to 3 space. Now let's look at some graphs. What if I want to graph an equation? And I'm going to start with the equation of the form x equals a constant. In 2 space, you probably recognize that as a vertical line. Let's just do x equals 2. That would simply be a vertical line with an x-intercept of 2. I'm actually going to write something down here in a very particular way because I want you to see something as we look at the parallel situation over here. Instead of calling that a vertical line, I'm just going to make the remark that this line is parallel to the y-axis. All right, what would x equal 2 look like in 3 space? Well, here we got that vertical line because every single point on the line, no matter where we looked at it, all had the same x value, right? It was always 2 comma something. I need that same situation in 3 space. I need all the points with an x value of 2, but the y and the z could be anything. what's going to happen is we're going to get a whole plane. Here's x equals 2. I'll just indicate the x-intercept there. And if I were to draw, this is intended to be a plane surrounding it, every point in that plane has coordinates. 2 is x, and there's some y and some z. The y and the z will be different for all these points, but the x value is going to be 2 every single time. So we're going to get a plane in 3 space. And notice this plane is parallel to the YZ plane. It's perfectly vertical. So look at the pattern. X equals 2 here was parallel to the y-axis. X equals 2 here was parallel to the YZ plane. So that was the opposite variables, right? Let's use that same idea to draw a couple of other planes. Next one, I want the equation y equals a constant in 2 space. If I just were to graph, let's say, y equals -3, it would be a horizontal line. Okay. Or I could write that as a line parallel to the x-axis. What's y equals -3 going to look like in 3 space? Well, the y-intercept, -3, would be over here. And then I would have all of the points with any x value, any z value, as long as I continue to let the y value be -3. That's going to give me a vertical plane. And again, I'm following my own advice here. Notice I'm drawing in such a way that I draw parallel to the axes to give me the perspective. Now, I'm not the world's best artist, especially in 3 dimensions, so don't worry if you're not either. It's okay. Give me a credible effort is all I'm asking. So there's that vertical plane, and we'll notice that it's parallel to the XZ plane. Again, watch that pattern. Y equals -3 was parallel to the x-axis. 3-dimensionally, y equals -3 parallel to the XZ plane. All right. I've got one more equation of this form. We've looked at x equals a constant. We've looked at y equals a constant. What about z equals a constant? Z equals a constant doesn't exist in 2 space since there is no z variable in 2 space. But in 3 space, if I were to, let's say, do z equals 5, there's the z-intercept at z equal 5. And this graph would consist of all of the points that have a z value of 5. X can be anything, y can be anything. So I'm going to end up getting a horizontal plane up here that's parallel to the xy plane. All right, there is one more. By the way, it's up to you what looks good to you. Sometimes just shading them in helps me focus a little bit and see it better. It's up to you when you draw these what you want to do. One more graph I'd like to take a look at. The graphs of circles and spheres. For right now, I'm going to stay centered at the origin. And let's just look at a simple circle like x squared plus y squared equals 4. It's just a circle of radius 2, right? That's r squared. So if I were to sketch it in, that graph is simply that circle of radius 2. To 3-dimensionalize this, actually let me just do a circle of radius 2. If I were to 3-dimensionalize this and add another variable, a z squared, The equation x squared plus y squared plus z squared equals 4 is going to be the three-dimensional version of a circle, what we of course would know of as a sphere. So let's sketch a sphere. I'm going to start in the YZ plane, the one that's flat in the plane of the paper, and just sketch the circle of radius 2. And then this circle becomes a sphere by giving it three-dimensionality. It's a little bit hard to get the perspective perfect, so what I usually do when I draw a sphere is I just sort of generically add an equator line in there. I don't try to actually get the exact value of 2 to come out in my perspective. Should be very clear to my reader that the radius is 2. They can see that on the y-axis. They can see that on the z-axis. So we're fine. All right. The last thing I'm just going to mention here is circles, and by extension spheres, you know can be shifted. So I'll just note, if I had x minus h squared plus y minus k squared equals r squared, that of course would shift, so my circle now would be centered at hk. And the same idea here. If I were to have a third variable, let's call it n. That shifts the center to hkn. So certainly you can shift these things just like you shifted in 2 dimensions. All right, we'll end part 2 there, and I will invite you to come back one more time to part 3. In part 3, we're going to look at the notation that's necessary to graph three-dimensional objects in Maple.